G'day, this video is on anti-differentiation of trig, trig functions, I guess. Anti-differentiation of trig functions. And what we're going to look at is integrating things that look like, sine squared x times cos cubed x and things like that. How do we do these things? Things like cos to the power 4x dx. We haven't come across this yet, and we've got no way of doing this. There's no direct way of doing it, and what we have to do is just rearrangement and moving things around, trying to reduce these powers. So basically, the aim of it, because we don't know how to integrate with these powers, there's no chain rule for anti-differentiation. What we want to do is reduce those, make those numbers smaller in order to be able to get it into something so that we can anti-differentiate it. And what we use is a bunch of different things. We use a rearrangement of if we arrange one of the double angle formulas, then what you get is that sine squared x is equal to 1/2 minus a half cos 2x. So that's a rearrangement of double angle formula for cos 2x. Also we've got cos squared x, similarly, is half plus a half cos 2x. So I've got that. And the other ones that you know already, things like from the Pythagorean identity that sine squared x is equal to 1 minus cos squared x, and cos squared x is 1 minus sine squared x. So they're probably the main players, that sort of identities that we use to be able to reduce these powers down. The other ones to remember are your things like 1 plus tan squared x equals x squared x. So remember that one as well. Just remember any of your trigonometric identities, and if you can use those to reduce the powers and to get it into something that we can anti-differentiate. So the main thing I'm going to do is just show you a few examples, but in class I've given you a sheet, a guide on what to do and when to do it. And so I would follow along with that, with these videos, with that big sheet of paper that shows you what to do. So I'm just going to run through some examples. Okay, some example, integral of cos squared x, something nice and easy like that. Okay, so we don't know how to do this. We don't know because of the squared power, but can we reduce that squared? Well, what we can do is we can rewrite it. Instead of cos squared x, what we can change it, using that double angle formula, we can go half plus a half cos 2x dx. Okay, and by doing that, we haven't changed the value of it, it's just these two things are equal, but now it's in a form that we can anti-differentiate. So now that we anti-differentiate that, integrate 1 over 2 is half x, or x over 2. Anti-differentiate this, cos goes to sine, so it'll be plus a half sine 2x, but then we need to divide by 2 as well, so times another half there, plus c, and we'll just clean that up, x over 2 plus 1/4 sine 2x plus c, and there's your answer. So what we need to do, we reduce the power. See how we started with a power of 2, and we reduced that to a power of 1 there. So we've reduced the power, get it to something you can anti-differentiate, and then do it. So that's your first example. Next one, let's do, I might not, with some of these examples, I might not do the whole problem, but I'll just show you how to get started, because I'll just run out of time if we do that in one of these videos. Okay, so something like that, sine to the power 4x. Well, what you need to do is realise that that is sine squared x squared, so like that, and then from there what you do is you replace sine squared with its double angle formula, which is half minus a half cos 2x, and that's squared, and then you need to expand that out. So something like, so if you expand that, you get half squared, which is a quarter. This times that is negative a quarter cos 2x times 2, negative a half cos 2x. We're just expanding this perfect square here, plus 1/4 cos squared 2x dx. Okay, so what we've done is we've started with a power of 4, we've reduced it to a power of 2 here and a power of 1 there. Okay, so we'll reduce that. That's good. Can we anti-differentiate this yet? Well, we can have, yes, we can do that. Yes, we can do that. At this stage, we cannot do that. So what do we need to do? Go again. We need to replace that again. So that's equal to the integral of a quarter minus half cos 2x plus 1/4, and in the brackets we're going to replace cos squared 2x. What will that be? That'll be a half plus a half cos, but we need to double the angle 4x. Like that. Okay, equals, and I'll expand it one more time. 1/4 minus, minus half. No, I'll do it one go. Sorry to waste your time there. 1/4 plus 1/8 here. So that's 2x plus that's 3/8 minus a half cos 2x, and then plus 1/8 cos 4x dx. You hear my wife sneezing. Equals, and then we can integrate. I might as well just do it. That's 3x over 8. Cos goes to sine, so minus sine 2x, but then we need to divide by 2, so that'll be a quarter instead of a half. And then here we've got plus, cos goes to sine, so it'll be sine 4x, but we need to divide by 4 as well, so that's 1 over 32 plus c. And there's your answer for that one. Okay, so that's what we do in that case. Let's. I'm just going to quickly run through a couple of these so you can sort of just see generally what happens. Integral of, let's do an odd power, so let's do cos to the power 5. I should do 3, just for simplicity I'll do 3, so it doesn't take quite so long. Cos cubed x dx, what do we do there? Now if you have an odd power here, what you can just do is take out or strip out one of the cosines. In other words, write it as cos squared x times cos x dx. What we've done is we've stripped one of those cosine x's out, and what we want to be able to do is to be able to use the u substitution. In other words, we want something in here to have its derivative as cos x, and what that's going to be is sine x, because the derivative of sine x is cos x. So what we want to do is change this to sine x. We can change cos squared x to sine x by making that 1 minus sine squared x, that's equal to cos squared x times cos x dx. Now what we have is we can say let u be equal to sine x. That makes du dx, derivative of sine x, equal to cos x. Okay, so that's our little junk there. So that's equal to the integral of what we got here. This is 1 minus u squared. Cos x is du dx times dx. That cancels. And what we have is just the integral of 1 minus u squared du. And I might as well just finish it off. So that's equal to u minus 1/3 u cubed plus c. And if we put x back in, that's sine x minus 1/3 sine cubed x plus c. And that's how you do that one. Okay, so that's all good. Let's have a look at another topic example. Might be able to I'll just check my time because I just can't go too much. Up to 8 minutes, it's okay. I'll just do one more example, I think. Let's do integral where we've got select sine squared x cos cubed x dx. Okay, so again, when you've got this type of situation, you've got an even power here and an odd power here. What you want to do, the odd powers help us a lot, because when you strip one of those out, then you're left with only even powers, which you can clean up with 1 minus sine squared or 1 minus cos squared. So that's what we want to do. We want to strip out one of those even powers. So let's rewrite that as sine squared x times cos squared x times by cos x dx. And now what we have here is cos x, and so what we only want to have here is just sine x's in here. Don't want to have any cos squared x, just sine x, because when we do our u substitution in here, u is going to be sine x, so we don't want to have this cos squared x left here. Okay, so just to show you, this is going to be your du dx here, and there'll be a u squared there when we have sine, but we want to make that into sine x somehow. Okay, so what this is equal to sine squared x, and we'll change cos squared x into 1 minus sine squared x times cos x times dx. Okay, so there we go. So now we'll do the substitution. We'll say let u be sine x, du dx equals cos x. And so what happens is that this is equal to the integral of u squared, bracket 1 minus u squared, times du. I'm not going to do this anymore, but cos x is du dx times dx, it's just du. So what that's equal to, expand that out, u squared minus u4 du equals, shouldn't be doing this, 1/3 u cubed minus 1/5 u5 plus c. Put your u back in, 1/3 u was sine cubed x minus 1/5 sine 5th x plus c. And that's how we do that one. I'll just try to quickly do one more example, but that's what you do when you have an odd power. Okay, if one of them's an odd, strip out that one and you can use your substitution. I'll quickly get time for one more, I think. And so, what happens when both of them are even though? So let's just look at that. Let's do the easiest of them. Sine squared x times cos squared x, something like that. Alright, dx. If both of them are even, you're just looking for combinations of different double angle formulas and that sort of thing. So what we can do here is write that as sine x cos x squared dx. Okay, so we've got something like that. And then what we can use is the identity. Remember that sine, let's put it in here, sine 2x is equal to 2 sine x cos x. That's one of our identities from Trig. So what this inside thing is equal to is half sine 2x. Okay, so that's equal to integral half sine 2x all squared dx. And so I'll just do this, so that's 1/4 sine squared 2x dx. Still, we've got a squared power here. We're still not out of jail yet, but what we can do now is use our double angle formula, the other double angle formula. So that's 1/4, and in brackets we'll write here 1/2. It's sine, so it's minus a half cos, and we're doubling the angle, so that'll be 4x, like such. And I won't go any further because I'll run out of time. But what you need to do next is just expand that, and then integrate. You can integrate from there. Oh, I might as well finish it off. So that's x over 8 minus 1 over 32 sine 4x plus c. There's your answer there. Hope that helps. They can be quite tricky, but if you follow the rules and follow that sheet, they're no problems at all.